Okay, last lesson we started to learn a little bit about radicals, and so this lesson is going to go into more detail, and we're going to learn the correct terminology that goes with our radicals. So this symbol right here is what we call the radical symbol, and this number that goes in here, we learned this last time, that's the index number or the root. So we could call it index number or root. And then what's underneath here, this is called, whatever number is underneath here, we were using that as our base last time when we were rewriting. Well, that's called the radicand. So whatever's underneath there, variables, numbers, whatever's inside the radical, its term is called the radicand. And down below in this little sentence down here, it says, if blank is not written, it is automatically a blank. Okay, so it's if a index number or root is not written, it's automatically a 2. Remember, square root symbol. That is the square root. That we call that the square root symbol. That's how we name that. We say the square root of 7, something like that. The index number there is a 2. We just don't write it. It's understood to be a 2. Okay, so this one says for each radical, determine the index number and the radicand. Okay, so index number right here, that's our index number. So index number for this one is going to be 2. It's not written, so it's understood to be a 2. And the radicand is the 24. The one on the right, the index number is a 3, so this would be considered a cubed root. And the radicand is the 27. And down below, this root right here, the index number is a 4, so that's like a 4th root. You would read that 4th root. And the radicand is 16xy. Over here, this bottom one on the right bottom corner here, index number is a 2. Since we don't see anything written, the index number or the root is a 2. This is a square root. And then the radicand is 128 n to the 8th power. Okay, so this slide is getting us ready to teach us how to reduce our radicals. So this says, write all the factor pairs for the given number, then circle the pairs that contain a perfect square. So remember, perfect square numbers, I've got a list here. Perfect square numbers are these numbers right here. How do you create this list? Well, you take the number 1 and you square it. That gives you 1. You take the number 2 and square it. That gives you 4. Take the number 3 and square it. That gives you 9. So you just take your counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, square them, and it gives you the perfect square numbers. So that's how we generate that list. Now, when we're doing factor pairs, you want to do this in a systematic order. You don't just randomly want to think of, oh, numbers that multiply to give me 48. I wonder what those could be. Be systematic, and then you'll make sure that you get all the factor pairs. So for 48, I do 1 times 48, 2 times 24, 3 times 16, 4 times 12, 5 doesn't go into 48, 6 times 8, and then 7 is my next number. 7 times 7 is 49, and then you're back to 8. If you do it in a systematic order, kind of makes this U shape. You're starting down here, and then my factors start to repeat themselves up this way. So this would have been 7 times 7, which didn't work, and now we go up the other side for the other numbers. So if you're keep it in an organized fashion, it's easier to make sure that you get all of your factor pairs. Okay, so after you get all your factor pairs written, you want to be able to identify out of those factor pairs which ones are perfect square numbers. Well, 16 is a perfect square number. That's on our list, so this has a perfect square in it. 4 is a perfect square number, so there's another factor pair. Okay. Next one over here, let's do 20. So 20 is going to be 1 times 20, 2 times 10, no 3, 4 times 5, and now I'm back to all my factor pairs. This one, the only perfect square number that's a factor pair is the 4, so 4 times 5. And then over here, 80, I already have this one worked out. Here's all of our factor pairs, 1 times 80, 2 times 40, 4 times 20, 5 times 16, and 8 times 10. Okay, once you've figured out all your factor pairs, what you want to do is you want to look for the biggest perfect square number that you've circled. So if I'm looking at question 20 or number 24, I only circled 1. So if I were going to reduce a radical, which I'm going to show you how to do next slide, I would pick this factor pair, 4 times 6. 48, I have 2 choices to pick from. I have a 3 times 16, that has a perfect square, and I have 4 times 12. 4 is a perfect square. Okay, you want to pick the highest perfect square possible. So if I were going to reduce this one, I would pick 3 times 16 as my factor pair. 20, I don't have a choice. There's only one factor pair that has a perfect square. And then 80, same thing. I've got 4 times 20 and 5 times 16. You want to pick the factor pair that has the biggest perfect square number in it. So I guess I would pick the 5 times 16. So once you've figured out what factor pair you need to use, then you can reduce from there. So let's see how that's going to work. So here we are. We're doing our 80. These are the numbers that we had from the previous slide. So here's our perfect square numbers. Remember, I had 4 times 20 and 5 times 16. So my statement was I want to use the one with the biggest perfect square. So I'm going to use 5 times 16. So what you do is you take your radical symbol, and instead of writing 80, write the factor pairs that it multiplies to be. So I'm going to actually do the 16 first times 5. Okay, so 16 times 5. You could do 5 times 16 instead. I'm going to do 16 times 5. All right, once you've written that factor pair, you could write this as 2 separate factor radicals. So you could go square root of 16 times square root of 5. That's true. I could write it under one big radical, or I could separate it out into 2 different radicals. Well, if I separate it out into 2 different radicals, then I know what the square root of 16 is. The square root of 16 is 4. And then I would have a square root of 5. So that is, it says, so square root of 80 in simplified radical form is 4 root 5. That's the answer I would be looking for if I wanted simplified radical form. Okay, what happens if you pick the other one? What if you did the 4 times 20? Okay, so let's work through that. It says which one is less work? Well, let's see. If I did 80 and I wanted to do the 4 times 20, okay, so I know that I'm going to do 4 times 20. Then that's going to be the square root of 4 times the square root of 20. Well, I know the square root of 4 is 2 and square root of 20. You should get the same answer. So it shouldn't matter what factor pair you use. You should get the same answer in the end. So now I'm going to have to take a closer look at 20. What are all the factor pairs of 20? Well, we did that on the other slide. 1 times 20, 2 times 10, and 4 times 5. Which one had the perfect square in it? 4 times 5. So now I'm going to have to rewrite this as 4 times 5. And then the square root of 4 times the square root of 5. Well, the square root of 4 is 2. So since there's a number out in front already, you're going to have to multiply it together. So 2 times 2 is 4. And you end up with 4 square root of 5. End up with the exact same answer, which you should. Which one was less work? The one that had the biggest perfect square factor. So that's what you're going to want to look for, is the biggest perfect square factor. If you don't know and you're like, oh, this is too much work to write out all these factor pairs, I don't want to find the biggest one. Okay, well, then I usually check for 4s and 9s. Those are 2 common numbers. See if your number divides by 4. See if your number divides by 9. I know what the square root of 4 is. I know what the square root of 9 is. So I usually try to simplify them using 4s and 9s. Okay, alternate method is called prime factorization. So this one is not my favorite. I do use it every now and again. I tend to do the perfect square factors. But if you were going to do prime factorization, then what would happen is this. You would start to do a factor tree basically. So off the top of my head, 80 is 8 times 10. Then 8 would be 4 times 2. And then 10 would be 2 times 5. And then 4 would be 2 times 2. So prime factorization of this is 2 times 2 times 2 times 2. So we got 4 2's times 5. That's its prime factorization. You could write 2 to the 4th if you wanted. I'm going to leave it like this just so that we can see how to reduce it. If you have an index number here of a 2, so or a 3 or whatever the index number is, you need to have that many of the same factor pairs. So for example, there's a lot of 2's going on here, but the index number is 2, so I need to have 2 2's. Okay, I do. I have 2 2's here. Do I have 2 5's? No, I don't. So basically what we're saying is this. 2 times 2 is 4. What's the square root of 4? 2. So I bring that one out. I've used those two. 2 times 2 is 4. What's the square root of 4? 2. Bring that out. Can I reduce the 5? No. And then 2 times 2 is 4, root 5. So still got the same answer as we did on the other slide. So that's the prime factorization way. I don't use that way very often. I do use it sometimes. Sometimes it's a little more helpful. But I tend to do the perfect square factor. That's kind of what I want you to do here on this one. So this one says no calculators. So we're going to try to reduce this radical into its simplest form without a calculator. So we've got to do either all of our factor pairs. So like I said, some of you guys may not want to, I don't want to write all these out, too much work. Okay, if it's too much work, try to think of a 4 and a 9. Those would be my first two choices. If it had a 5 in it, I might think 25 and maybe 16 if I couldn't get something to work. But I usually try 4's and 9's first. So instead of, if I didn't want to write out these factor pairs like I've done here, I would maybe look at this at 20 and I recognize right off the bat 4 times 5. 4 is a perfect square. It's on our list. 4 times 5 is 20. So if I'm going to rewrite that, that's the square root of 4 times 5. What's the square root of 4? 2. And then the square root of 5 stays there. Okay, so 24. Instead of writing down all the factor pairs, I'm just interested in the factor pairs that have a perfect square factor. So I know that 24 is divisible by 4. So 4 times 6. That would give me the square root of 24. Okay, so I'm going to reduce that. That's going to go 4 times 6. What's the square root of 4? 2. So 2 comes out, and the 6 stays there. Square root of 25, we should know that one's 5. Okay, 32. So off the top of my head, the first thing that pops into my mind is 4 times 8. 4 is a perfect square, but remember, we want to pick the biggest one. I also recognize that 16 times 2 is 32. So I think instead of doing the 4, you could do the 4, we'd have to do it twice. I'm going to use 16. So I'm going to go 16 times 2, that's the square root of 32. Square root of 16 is 4, 4 root 2. Okay, those of you that thought of 4 times 8, not wrong. You would just write your problem like this. 4 times 8, square root of 4 is 2, and now you have 2 root 8. Well, the answers are supposed to be the same. That must mean you got to do it again. Well, 8 is 4 times 2. So square root of 4 is 2. There's already 2 there, so you have to multiply it, and you end up with the same answer. It's just less work if you can pick the biggest perfect square factor. Okay, 165. So I said no calculators, meaning I don't want you to type in the square root of 165. If you wanted to get your calculator out to see what a factor pair of 165 is, that's okay. I'm looking at 165. I don't even know if 4 or 9 divides into that. There's those little tricky rules that you guys might have remembered back from 6th or 7th grade. I think you teach you those. I don't remember what they are, but I do know it ends in a 5. So 165 divided by 5 is 33. So if I'm looking at this, and this would be one case where I'd actually do the prime factorization. This is 5 times 33, and I know that 33 is 3 times 11. That's prime factored. There's no perfect square factors for 165. So in its simplest radical form, it's the square root of 165. Okay, so here, same thing. It says, give an exact answer and approximate answer. Okay, you need to understand the difference between exact and approximate. This is the most missed concept on tests from here on out all year. I will say, give me an exact answer, and people will write me a decimal. And they'll tell me, but I rounded it right. No, decimals rounded are approximate. That is not an exact answer. So if I want an exact answer, it needs to be as a fraction. It needs to be written as a reduced radical. I can have a decimal as long as the decimal terminates. So, for example, exact answer, 1/2 in decimal form is 0.5. That's okay. 1/3 is exact. 0.3, repeating 3 is not exact. I don't care if you rounded it correctly or not. If you write 0.3, that's not exact. That's approximate. So you got to know the difference between an exact answer and an approximate answer. Okay, so here we go. We're going to do square root of 12. So like I said, I like to do perfect square factors. Off the top of my head, I always think 4s and 9s right off because I know the square root of 4 and I know the square root of 9. So 12 is 4 times 3. So this is the square root of 4 times 3. What's the square root of 4? It's 2. So 2 root 3. So my exact answer is 2 root 3. Okay, this is where you get to use your calculator and tell me what the decimal is. Okay, so I'm going to type in 2 square root of 3 and find out what that decimal value is. Well, it's going to be 3 point, and we'll go to 2 decimal places, 3.46. That's an approximate answer. 2 root 3 is exact. 3.46 is approximate. Okay, next one, square root of 18. Off the top of my head, the perfect square factor that pops into my head is 9 times 2. 3 times 6 is not helpful. I don't know what the I would not pick 3 times 6. I don't know the square root of 3 and I don't know the square root of 6. So I'm picking 9 times 2. Do I know the square root of 9? Yes. Square root of 9 is 3. And then I have the square root of 2 right there. So the exact answer is 3 root 2. Okay, type it in your calculator. See what the decimal value is. It's 4.24. Okay, square root of 48. Off the top of my head, I'm thinking 4 times 12, because I know that 4 goes into 48. But I also know I got 4 times 12, but I also have 3 times 16. I'm going to use 3 times 16. 16 is the biggest perfect square factor. So I'm going to go 16 times 3, square root of 16. I know that answer is 4. And then the 3's here. So my exact answer is 4 root 3. And my approximate, let's figure out what that decimal is. So square root of 48, 6.93. Approximately. Okay, square root of 128. So like I said, I try to think of 4s and 8 or 4s and 9s if I don't want to do all the prime factor pairs. I know that 4 is going to divide in there. Let's just see if 9 does. Nope. What about, just curiosity, what about 16? Yeah, ooh, it's even got more than that. If I did 16, this is 16 times 8. Let's just go ahead and go with that, and we'll do it twice. That one, those pop into my head. 4, 9, and sometimes I move to 16. So this one right here would be 16 times 8. Square root of 16 is 4. And then 8, but I know that 8 is 4 times 2. And so that's 2. Square root of 2 is, or square root of 4 is 2, and 4 times 2 is 8, so I end up with 8 root 2. Oh yeah, duh. How many of you guys recognized right off the bat that this was 64 times 2? So much faster. 64 is a perfect square. I should have recognized that. So I could have done 64 times 2. Square root of 64 is 8 root 2. So much faster. So much faster. So if you can find the biggest perfect square factor a whole lot faster to solve those problems. And then our decimal equivalent is 11.31. Okay. How do you simplify something if it's not a square root? So if it's a square root symbol, we look for perfect square factors. If it's a different root, you look for perfect cube factors. So what are the cube numbers? Well, if you take 1 and raise it to the third power, you get 1. If you take 2 and raise it to the third power, you get 8. If you take 3 and raise it to the third power, you get 27. 4 raised to the third is 64. 5 raised to the third is 125. 6 raised to the third, I think, is 216. Let's double check that. Yep. 7 raised to the third is 343. 8 raised to the third, I'm not sure what that one is. 8 raised to the third is 512. 9 raised to the third is 729. And 10 to the third is 1,000. Okay, so you do the same idea here. Look for numbers on this list that multiply to give you 32. So I think on this list, I would pick 8. 8 times 4. Okay, so I'm going to do the cubed root of 8 times 4. So what is the cubed root of 8? The cubed root of 8 is 2, because 2 to the third is 8. So the 2 comes out, cubed root here, and 4 left right there. That's our reduced radical right there. Okay, 56. What numbers do we want to use for 56? What I was thinking, 56. How about 8 times 7? Cubed root of 8's a perfect cube number, so we got cubed root of 8 times 7. What's the cubed root of 8? It's 2. And then you're left with cubed root of 7. Okay, so what about fourth roots? Well, you do the same thing. You would try to figure out perfect fourth root factors. So 1 to the fourth is 1. 2 to the fourth is 16. 3 to the fourth is 81. 4 to the fourth is 256. And 5 to the fourth, that's as far as we'll go because that's plenty big. We won't have numbers that big. 625. Okay, so it looks like to me then, I'm not going to pick 4 times 8. This is a fourth root. Pick a number off of this list. So this time I'm going to do 16 times 2. So I want the fourth root of 16 times 2. Okay, what is the fourth root of 16? It's 2. And so you end up with 2, oops, I wrote a 2. I want a fourth root. Too many 2's. 2 fourth root of 2. Okay, this one says simplify the following radicals, leave answer in reduced radical form. Okay, so this would be something where in class I would just let you work on this. We'll go ahead and just quickly write the answers here. Lots of things multiply to give us 48. I'm going to do 16 times 3. So you've got square root of 16, which is 4, so that's 4 root 3. 54, what goes into 54? Let's see. So 4 doesn't go into 54. I'm usually looking for 4s and 9s first, and then 9 does. So 9 times 6 is 54. So I'm going to do square root of 9 times 6. So square root of 9 I know is 3. And so we end up with 3 root 6. Okay, down here, cubed roots. So remember, cubed roots, I'm looking for a 1, an 8, 3 to the third is 27. So I think on this one I'm going to do 8 times 6. So this is the cubed root of 8 times 6. What's the cubed root of 8? It's 2. So you end up with 2 cubed root of 6. 54, I'm going to use 27 times 2. So we're going to have the cubed root of 27 times 2. What's the cubed root of 27? It's 3. So 3 cubed root of 2 is the final answer. Okay, what happens when there's a number already out in the front? We've kind of already talked about this. If you have a number out in front, you just multiply by that number. So right here, I'm going to do 4 times 2. So this is going to be square root of 4 is 2. I bring that out and multiply it. So 2 times 3 is 6. So 6 square root of 2. Over here, once again, I'm going to do 4 times 3. Okay, what's the square root of 4? It's 2. So I'm going to bring the 2 out and multiply it by what's out in front. And so 2 times 7 is 14. So you get 14 square root of 3. Okay, 24. I'm going to do 4 times 6. Okay, I'm going to kind of shortcut this now, guys. I'm going to cut down a step. Instead of rewriting the next step instead of doing this, I am going to just do this in my head. What is the square root of 4? It's 2. Bring the 2 out. Multiply it by what's there. 2 times 5 is 10. What's left over in my radical is 6. Okay, cubed root. I'm going to do the same thing on this one. I'm going to use 8 times 3. So what is the cubed root of 8? The cubed root of 8 is 2, so the 2 comes out in front. 2 times 4 is 8. And then I have the cubed root of 3 left over. So I'm going to kind of start shortcutting my process here instead of writing down every step. So practice, no calculator. So that means I just don't want you to type in the square root of 105 and give me the answer. You got to work it out. So on your homework, you have to show what factor pair you used to get the square root of 105. So 105 is 5 times 21, and this one I'll go down to prime factorization so that you can see there are no perfect square factors in that. So square root of 105 is its simplified form. Okay, 96. We need to figure out what goes into 96. So you could try 4. 96 divided by 4 is 24. So it looks like to me maybe 16. So 96 divided by 16 is 6. So let's do 16 times 6. Okay, so we're kind of shortcutting it now. What is the square root of 16? It's a 4. That comes out in front. 4 times 2 is 8. And then what factor pair did I not use? It was the 6, so that stays under the radical. Okay, cubed roots. This one, cubed root of 64 is 4, because 4 times 4 times 4 is 64. And cubed root of 128, I will do 64 times 2. And cubed root of 64, we just did over there, is 4. And what stays under the radical is a 2. Okay, what happens when they're variables now? And then can we figure out a pattern so we can do it quickly? This one I like to do as prime factorization so that you can see how it works. So underneath here, this would be x times x. If you want to bring an x out from underneath a radical, you need to have the same amount of x's or variables as your index number. So the index number there is a 2, so I have to have 2 x's. Well, I do. So when you bring them out, though, you don't bring them out as x squared. You bring them out as what times what gives you that? Well, it's the x. So this one turns out to be x. So right here, if I was doing x to the third, this would be x times x times x. Well, there's two of them here, right here. So that comes out as x square root of x. Okay, next one, I've got 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so remember my index number is a 2, so I need them in sets of 2. So here's this one, this one, this one, this one. So when I bring this first one out, that comes out as an x. Then I do the next one. That comes out as an x. Then I do the next one. That comes out as an x. And then I do the last one. It comes out as an x. So x times x times x is x to the 4th. All right, x to the 10th. Faster way to do this. Let's see if we can figure out the faster way. My index number is a 2. So 2 goes into 10 5 times. I bet there would be 5 sets of x times x. So there would be 5 sets of x squared. So when this comes out, this is just x to the 5th. Okay, let's try another one. Let's do x to the 13. Well, index number is a 2. How many times does 2 divide into 13? 6. So I know there has to be at least x to the 6th, but there's 1 left over. So what happens, guys, is underneath your radical sign, whatever this index number is, right here, this one's a 2, the power underneath the radical sign, if you're simplifying, has to be less than that. So that power was a 1, so that's okay. So if I have an index, a number of a 2, so any square roots, if I'm reducing those variables, the highest power that I can have under the radical is a 1. Okay, with that same idea, then if I'm going to reduce a cubed root, then I bet the highest power that I can have underneath there, it has to be a 2, a 1, or I guess we'll just say 2 or 1, because to the 0 power would just be 1. Okay, so if we did prime factorization of this, this would be x times x. The index number is a 3, so that means you need to have 3 identical factors. I do not have 3 identical factors, so this one is reduced. The cubed root of x squared is just x squared. Okay, what is the cubed root of x to the 3rd? Well, there are 3 identical factors, so the cubed root of that would be x. X to the 8th, we'd have 8 x's. Okay, and we would do them in sets of 3 since my index number is a 3. So there's 3 of them here, 3 of them here. So that would equal x squared with a remainder of x squared, because x times x is x squared. So without doing this one longhand, I would do the same thing I did over there. I would take the 3 and divide it into 10. 3 divides into 10 3 times evenly with 1 remainder. So let's try another one. Let's do cubed root of x to the 17. Okay, well, 3 divides into 17 5 times, because that would be 3 times 5 is 15, and that would give you 2 left over. And that would go right there. Okay, so that's how you reduce radicals. So here's a quick check that has everything together, numbers and variables. So square root of 32, once again, we want to look for perfect square factors, so I'm going to do 16 times 2. I know what the square root of 16 is. It's 4. So I'm going to write the 4 out in front. I'm going to draw my radical symbol because I know the 2 has to stay inside. Okay, now I'm going to come and look at my numbers. X squared. What is the or variables? What is the square root of x squared? It's just x. Okay, that's taken care of. Okay, what is the square root of y to the third? So what if we just had square root of y to the third by itself? What would that be? That would turn out to be y square root of y. So y comes out and y stays inside. So that's our answer. Okay, over here, we're just going to work left to right. So to start with a number, what is the cube root of 64? It's 4. So I'm going to bring that out. And now I've got x to the 8th. So it's just like saying, what's the cube root of x to the 8th by itself? Well, 3 goes into 8 2 times with 2 left over. Okay, and now we're going to move over to the y. So now we're doing the cube root of y to the 6, just like we were doing that by itself. Well, 3 divides into 6 2 times, so it's y squared, and that's our answer. So 4x squared, let me rewrite that better, 4x squared y squared cubed root of x squared. That's what it reduces to. Okay, last idea is combining our radicals, so meaning adding and subtracting. So on this slide here, we just kind of have a visual. So I've got 2 red apples. I guess we call those apples. You add them together, and you get 2 apples. So over here, even though these are fruit, so you could say they're kind of like a radical, you can't combine the apple with the pineapple. It just stays an apple plus a pineapple. That's the same thing with radicals. So what they're saying is something like this. Square root of 2 plus square root of 2. Those are identical, right? Well, that means I have 2 square root of 2. Over here, it would be something like saying square root of 3 plus square root of 5. Square root of 3 is different than the square root of 5. You can't add those together, so you just have to leave it like that. Okay, so let's practice. So you have to have, in a nutshell, the rule is you have to have the same index number and the same radicand in order to add or subtract your radicals. So I'm looking here, index number, same index number. Perfect. Index numbers are the same. So that's the first thing you want to check. Then you want to check radicands. Do they have the same radicands? They do. They're both 3s. So what is 4 root 3 plus 2 root 3? Well, 4 plus 2 is 6. And then you leave the radicand alone. So you don't add the radicands, you just leave them alone. It's like saying the 1 apple plus the other apple is 2 apples. Leave the radicand the same number. Okay, down below, quick check. Index numbers and then radicands. They're the same. So just subtract the numbers out in front. So 4 subtract 6 is negative 2, square root of 7. Okay, next one, quick check. Same index number. Different radicands. They have to be the same radicands. So now, that's why we spend all this time reducing radicals. You got to reduce those radicals, get them to be see if they'll be the same. So square root of 24, I think, is 4 times 6. So square root of 4 is 2 root 6 plus 54, 9 times 6 is 54. So square root of 9 is 3. And then you're left with square root of 6. Okay, now you can add them together. I have the same index number and the same radicand. So 2 plus 3 is 5. Square root of 6. Okay, this one is the same as the one above. It's just that there's numbers out in front, so just reminding us what we do with our numbers. So square root of 4 is 2. Bring that out in front here. There's not room to write it, but 2 times 4, so that's 8. Square root of 6 plus square root of 9 is 3. Already a number there, so 3 times 3 is 9. And then square root of 6. So 8 plus 9 is 17 root 6. Okay, so here's a few other practiced ones. So quick check. Same index number, different radicands, so you got to fix that. So this one is a cubed root, so I'm going to pull a number off our cubed root list, so I'm going to do 8 times 2. So this is 5, cubed root of 2, minus cubed root of 8 is 2, cubed root of 2. Are they both cubed roots of 2? Same index number, same radicand? Yes. So 5 minus 2 is 3, cubed root of 2. Over here, we have different index numbers. Okay, different index numbers. We have the same radicand, but different index numbers, so we're not going to be able to add those. Answer is 2 root 3 plus 5 cubed root of 3. That's simplified. Okay, is it any different with variables? You just still have to check the radicand. Have to have the same index number, same radicand. Okay, this one has the same index number, has the same radicand, so 2 plus 1 is 3. So this is 3, the square root of 3x. Over here, same index number, yes. Different radicands. So we're going to have to do some work to get them to be the same radicand. So I'm going to use 4 times 3 here. So I know the square root of 4 is 2. And that's going to leave me with a 3w minus, okay, I'm going to do 9 times 3 here. I know the square root of 9 is 3, so that's going to come out. And the 3 is going to stay inside with the w. Check again, same index number. Index number didn't change, only the radicands did, and they're now the same. So 2 minus 3 is negative 1, square root of 3w. Okay, so as a refresher, if you're going to add and subtract radicals, the rule is you got to have same index number and radicand. If you do, you can just combine them like you combine like terms. It's kind of like the same idea. Okay, next time we're going to learn how to multiply and divide radicals. So we know how to simplify them and we know how to add and subtract.